In the previous class, we were looking at the quadripace PSK, where four different symbols were supposed to be sent using two different carriers. And we saw that four different symbols are supposed to be sent using this particular equation SI of t with I varying from 1 to 4, and we used grayscale coding for those the change in the bits of such signals. Okay, and I think the phases are already shown here, and then we converted the SI of t into the required format just to extract the phi of t, right? The phi of t represents the orthonormal basis function using which, right, we can try to send the signals. All right, so there are two phi values, two phi functions, phi1 and phi2, and you can see that these are the two equations of the phi. Then we try to get the space coordinates of the symbols we are going to send for different values of phi. We made a table, and S1, S2, S3, S4 are the time domain representation in terms of time. Okay, for different phases such as pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4, we can see that we got SI1, SI2 as the four different values. Those are the coordinates corresponding to 1, 0, 0, 0, 0, 1, and 1. Okay, like that. And later on, we actually plotted, right, the constellation diagram of the QPSK. Right. So also we observed that, as you can see here, the phi1 and phi2 are the two axes, the coordinate axis for this, and they are going to act like the region boundaries for the detection of these four symbols. This is what we have seen. Now we'll move on. A QPSK QPSK transmitter. So the transmitter has an input part which takes the input binary sequence. Let's denote that as BI. Okay, so this is the input. Binary sequence. Let's denote this as BI. So basically, it means either you are sending a series of zeros or ones. Right. Now, this binary sequence actually enters into the system and it goes into a demultiplexer. Right. Now the demultiplexer will generate, it's something like we split the signals into the even and odd sequence. So we have multiple sequences coming up, right? Maybe every two sets, you have to divide the incoming sequence into sets of two symbols, correct? Because 0, 0, 0, 1, 1, 0, 1, 1 are what we are looking for. So just to get that, we use a demultiplexer over here. Right, so it generates two different parts. Let's assume the first one, which comes from the top side, and another part that actually is generated from the bottom half as a different channel. Let's assume. Okay, so like this we get. So the top one, the top channel carries the symbols denoted by say B, O, I, and the bottom one will called as B, E, I. Okay, maybe odd and even. O for odd, E for even. Okay, of the inputs. So again, this consists of zeros and ones ultimately, right? At the same time, even the bottom part will contain series of zeros and ones. Okay, now depending upon what is the amplitude of each of the symbol, you need to convert the amplitude, or you need to shift the amplitude into plus root of e by 2 or minus root of e by 2. This is what we have seen, correct, in the theory part, right? So when we discussed about, right, the conversion of zeros and ones into the amplitudes, right, we saw that yes, we need to shift the amplitudes by certain amount. So for doing that purpose, we have the amplitude level shifter over here. Amplitude level shifter. So one amplitude level shifter will be located over here, and there will be another amplitude level shifter at the bottom channel. All right. Now, what are the various levels the output should be shifted to? Right. We are going to. I'll just write it in brackets. So one amplitude is plus root of e by 2, and the other one should be minus of root of e by 2. Right. Same thing holds good even at the bottom channel. So we'll write that plus root of e by 2 and minus of root of e by 2. These are the two different levels. So we are converting the sequences into levels now. So once you have the required levels available like this, what we can do is we multiply by either phi1 of t or phi2 of t according to our need, right? So because one symbol gets multiplied by phi1 of t, other symbol gets multiplied by phi2 of t, and there will be a difference, right? So in the equation we saw that there is a minus term coming up, so we'll use it over here. So first output, let's take this output from the top channel, and we need to multiply. So there is a multiplier, and the input to the multiplier will be the first function denoted by phi1 of t, which is one of the signal representation. Okay, so orthonormal basis function. That's what we multiply for the first channel, and for the second channel we have to multiply once again, but this time it's phi2 of t. So here it will be phi2 of t. Then we have a summation coming up. We are simply building this block diagram as per the equation, right? We already have discussed the equation. You can simply add the two components after multiplication of phi1 and phi2 that gets generated. So the sum output of this summer or summation block itself will be the QPSK. So QPSK wave can be generated easily by using this technique. So just refer back to the equation, compare this with the equation of the SI of t, right, which had two parts. Okay, so something into phi1 of t minus something else into phi 2 of t. So the same format we are trying to generate here by using this block diagram. So our next objective is to look at the demodulator. So next we'll see the coherent QPSK receiver. So let us assume that we are receiving the signal through an antenna. This is the signal which is coming up, and this is the antenna, and through the antenna, let us assume that we are picking up the signal. So I'll write here, this is the received signal. Let's denote that as x of t. Okay, so now since it is a coherent detection, we know that we should know the values of phi 1 and phi 2 directly, because both the frequencies, whatever frequencies we are using to generate the phi 1 and phi 2 will be known to you because it is coherent. So you can directly generate phi 1 and phi 2, right, and you multiply. So this signal gets divided into two channels now, and one channel gets multiplied with phi 1 and the other channel gets multiplied with the phi 2. So this is the first part, and let us multiply this with phi 1 of t. All right. At the same time, we have another branch coming down. So this is the other channel where we multiply with the phi 2 of t. Okay, so in the received signal, we have seen that if you multiply by phi, that term gets, if assume that there was a cos function and the phi 1 also has the cos here, and when I multiply cos into cos, it becomes cos square of that frequency, and that frequency, when I square it, I'm going to get a 1 plus cos 2 theta format. So that 1 will give me the original signal back, and the cos 2 theta can be eliminated by using a filter. Correct? High frequency component. Right. So we are going to apply the similar idea here. Okay. So, and whenever I do this, I multiply by the phi 1 of t, right? In the received signal component, if there is a phi 1 component, that actually gets multiplied with this to get that 1, which gives me the original signal back. So if you multiply by phi 1 and integrate with respect to time, right? Uh, that's one type of receivers, very standard receiver, right? So let's do that here. After multiplying with the phi, let's do the integration. Okay, I'll use integration 0 to t dt. Okay. The same thing we are going to use here. This is integral 0 to t dt. Okay, once you do that, then we have to use a sampler circuit. So we'll sample this at every t equal to t or t, right? Then the same thing happens even on the other side. This is going to touch this at every t equal to sampling duration. Now let us see. The top half is going to generate a sample value that is say x1, and the bottom channel generates another value that is x2. Now x1 and x2, because see, our intention is to generate two symbols now, because right, we are what we are trying to send, right, is a set, is a symbol that contains two binary bits. Now also I should generate them, right, in the same order which was used to send the signal, correct? So what we try to do here, we try to generate both the symbols by using, right, two separate decision devices. There has to be a decision device for the top part. At the same time, you need to have another decision device at the bottom. Okay. Now, we know that the most common threshold value is 0. Okay, if it is, anyway, this looks like the ASK demodulation, correct? Set the threshold to be 0 and take a similar decision. And previously we used a demultiplexer, correct? Now on the receiver side you will use a multiplexer. Just to combine the two different symbols generated by both the channels. Okay, so the one which comes from the top is it's that was denote it, we call it as in phase component or in phase channel. Let me write in phase. Okay, and the other channel is called as a quadrature. Right. So the final result out of the multiplexer is the binary sequence or the output binary wave. So this is the required basic block diagram of the QPSK receiver or demodulator. Like any of the digital modulation technique, this particular technique also has a probability of error associated with receiving a 1 or 0, right? So the average probability of symbol error denoted by PE is equal to, this is the error function, square root of EB by N naught. So here the EB represents the energy associated with one symbol, and also the N naught represents the power spectral density. Actually, since we are assuming a Gaussian noise, it is going to, the N naught by 2 will be the total what you call the variance, noise variance. All right, so we can measure that using even the power spectral density of the noise. So look at the general structure of a M-Array baseband system. All right. So that's the general idea. So we can apply that for to any technique we want. All right. So this is an baseband system. All right. Now, in the MRE technique, it's a block diagram basically. It basically represents how to use a M-array system, right, in general. And if we replace the particular transmitter and receiver by a specific modulation technique, it becomes like M-array PSK, right? You can go with that. You can actually change it to M-array FSK system like that, right? So just replace that particular transmitter block by, right, respective modulator, right? It becomes a MRE so and so system. Okay, right. So this one block diagram is sufficient just to understand what is MRE baseband, MRE modulation demodulation technique. Okay, okay, so we'll write a simple block diagram. The first component is it will consist of, okay, it consists of say input binary sequence. So let's denote this as BK. Now, this is the simplest format of the message, and this will be in terms of what you call ones and zeros. Straightforward message in the binary format, not coded one. So it's not yet coded, right? You are not, this particular sequence, what we are considering as an input, is not the coded format. It's not NRZ, it's not return to zero, it's none of them. You have to apply that in the next step to convert it into the required coded format according to your necessity or the need. Yes, this particular stream of ones and zeros will apply to the next stage, which will generate the required pulse as per the coding technique, right? So that's what is called as the pulse generator. Right, so this is given to this. The binary sequence BK is applied to the pulse generator, and the pulse generator generates the pulses in series, and that's what we are going to call as X of t. It's going to be continuous, right? So all the pulses you are generated are cascaded one after the other to get a continuous signal. That's why it is X of t. All right. Now, the whole function of transmission is encoded into a filter. Okay, so we call that as a transmitting filter. Transmitting filter, let's denote that as HT of F, T for transmission. So this is something like we are assuming the complete work done by a transmitter, which includes a modulator, right, is represented by a filter function, right? Let's assume X of t comes as input. You perform the required modulation, right, and convert the low frequency signal into a high frequency signal using a filter. Okay, and it actually converts your low frequency into a high frequency. That transformation will be carried out according to the requirement. It may be ASK, FSK, PSK, or even the MSK. There are many other methods, right? So anything you can use. Okay. Yes. Then the output of the transmitting filter is passed on to the channel. So let us denote the channel as HC of F. Okay, it's the channel's frequency response. This is given, and we know that the channel's output will be received by a receiver, right? Now we try to represent the job done at the receiver side by using another filter. Let's call that as a receiving filter. So we have a receiving filter, and the output of the receiving filter has to be sampled. Okay, so let us try to sample this like this. Now let's say this output is y of t. Okay, now you are going to sample at every t is equal to I times capital T. So we'll slightly modify the notation here. Okay, so that you get y of it. So I is integer, right? You can see that if t is the capital T is the sampling duration, so you try to sample the signal at 1t, 2t, 3t, 4t, and so on, isn't it? So just because of that, now we can say that we are trying to sample the signals out at y is at small letter t is equal to I times capital T, where capital T is the sampling duration. So that's the notation we use here. Okay, then this is applied to the logic device. With a thresholding device. Actually, threshold can be any level that we can set according to our need, right? And this will generate the final output, that is output binary sequence. So this will be generated at the end. Now uh, this actually represents the basic elements of the M-array baseband system. Okay, now whenever I say that uh, I'm using a M-array system, right? The output waveform x of t of a pulse generator has m distinct levels. So the important aspect is this. So this looks like very common communication channel itself, right, for us. But the specification is like this. So in M array system, the output x of t of, you can see output is this x of t is uh, the output of pulse generator. Okay, so the output x of t of pulse generator has m distinct levels. So you can see if you consider the say PSK, right? You can consider that as say if you consider QPSK, sorry, not just PSK. If you consider QPSK, you can say that the output has 4 levels, right? Because 4 different symbols are being transmitted, and you have 4 different levels. You can consider. Now you see, we are trying to say m different levels, right? So m can be any number, right? We can decide that, right? So since it has m distinct levels, this particular technique is called as M array modulation technique. You can use m different symbols to be transmitted, right? With m different levels at the output, okay, or the encoding. So when you code it, the pulse generator will generate m different levels. Now, so what happens? Each amplitude level at the pulse generator output corresponds to a distinct symbol to be transmitted. So m distinct levels. So I'll write each corresponding to each corresponding to a distinct symbol to be transmitted. So consider a scenario where my symbols are English letters, okay, like A to Z. In such case, if you are using M array modulation technique, right, irrespective of whether you go for ASK, PSK, FSK, doesn't matter, right? How many levels we require? We require 26 levels because there are 26 letters, right? Each distinct symbol that you are trying to transmit requires a unique level. It should not overlap because if say the level you assign for B overlaps with the level you assign for say Q, right? You see there will be a confusion on the receiver side. When you receive a particular level, whether it is for B or Q, there will be a difference. It's difficult to decide, correct? So such cases, right, where you are using m different distinct symbols for transmission, you need m different levels, right, of encode. So that particular technique is what we are looking right now. Let us say that capital T is the symbol duration, right? In the M-array baseband system, there is a specific name for the 1 by capital T. So normally we know that the capital T is the symbol duration and 1 by T will be a frequency term, right? But here we have a specific name given for that. Every M-array baseband system will call the 1 by T as the signaling rate of the system. So that's the speciality of the M-array baseband system. So I'll just write that if capital T is the symbol duration, this implies the 1 by T is always called as the signaling rate of the M-array baseband system. So this is actually measured. Anyway, we know that symbols per second is the standard notation here. So right, symbols per second. This is what is called as the baud, BAUD, baud rate. You might have heard of the word baud rate. So that actually corresponds to this. It's not how it basically measures how many symbols you are trying to send in a second. All right. Now, so let us try to give a equation for x of t. Right? What is x of t? X of t is the output of the pulse generator. Right? So therefore, the output of pulse generator, that is x of t. So x of t is equal to, we know that there is a amplitude, let's call it as capital A, into there is a pulse that is getting generated, right? Like a rectangular pulse. Each amplitude A is getting multiplied by a pulse, rectangular pulse, that is G. So you see, first symbol has A1 into it gets multiplied by a rectangular pulse, say G1. Okay, second symbol, say A2 is a different amplitude, gets multiplied by another rectangular pulse because its height may be different, correct? So you see that amplitude is different means its height gets changed, but the pulse that you are going to consider will get shifted by the capital T amount in time, right? So we can try to write it in this fashion. So A1 G1, 8 plus A2 G2 plus A3 G3 and so on, where G1, G2, G3 are the time shifted versions of the same pulse, correct? So I can try to write it in this way. This is AK, kth pulse, G of T minus KT, right? So you see first pulse A1, it's present at G of T minus 1 into T. Second pulse A2 is the amplitude, G of T minus 2 into capital T, and so on. You can see that there is a shift coming up, right? So this has to be added. So I'll write a summation. So you can take the K value from minus infinity to plus infinity. So I'll write the specific, what you call, the terms, the meaning of the specific terms. Right? So here the G of T is basically a rectangular, it's a rect pulse of unit amplitude, because there is a term AK to control the amplitude. So you just have to multiply that AK with 1 over here. So you consider the rect pulse amplitude as unity. All right. Then amplitude is 1 and T in duration. Right? The duration of the pulse is expected to be capital T. So that's what is the G of T. So something like if I have, say, this is the first amplitude. So you see second amplitude, but this width is always capital T. You see capital T, another level, capital T, another level, capital T, and so on. Okay. So this is what is this. And okay, let's talk about AK now, because AK is very important. We are trying to encode M different levels now. So AK, let's write what is AK. So AK is, it's a, it actually represents the amplitude. But if you see, let me assume the same example. Let me come back to the same example of transmitting English letters as the standard symbols. Right. When I try to send a text, whether it is valid or it's invalid word in English, right? Maybe it's simply random. I may send specific word, right? The letters of specific word. Okay, I may send that. Otherwise, I may send at random, like A, G, G, B, C, D, D, whatever, random. Okay. Irrespective of this, you can see if I assume each one level for each of the letters, each letter gets a unique level, then the AK value is the AK value becomes a random variable. Are you okay with that? Because what you say, you may send any one of the 26 letters at a given point of time. Anyone may come. It doesn't matter whether you are trying to send a valid English word, the letters of a valid word or not. Right? So that's why this AK I'm going to call as a discrete random variable. AK is a discrete RV for random variable, taking the values like this. So let's write the following values. So AK is equal to, let me write, this is plus or minus A, this is plus or minus 3A, plus or minus 5A, and so on. These values will be taken when M is even. Let's understand this later. First, let's write. Okay, so this is 0, then plus or minus 2a, plus or minus 4a. This is when M is odd. So let's assume that we have, say, M is equal to 4. Okay, let's assume M is equal to 4, which falls under the first category. This is a even number. Right. Now, it says that if M is 4, you have to send 4 different levels. Correct? Your data should contain 4 different levels. So you consider the first 4 levels: plus A, minus A, plus 3A, and minus 3A. So these are the 4 levels which you are going to use. Right? At the same time, if M is odd, in the sense, let's say M is 3. When M is 3, I should use only 3 levels. What are the 3 levels you are going to use? 0, plus 2A, and minus 2A. So you see, this is how you identify which levels I should use. Let's go for a quick example. Right, let me assume that the data I want to send is this is an example. My input binary stream is 0, 1, 1, 1, 0, 0. Okay, let's say 0. And if you want to make a group of 2 and check, right, because the one which we already have performed modulation for 4 different levels, correct? It was the group of 2 bits, correct? So that's why I'm taking this example. If at all I want to do this, now I can understand from this is that the number of levels should be 4. So when I say the number of levels should be 4, this falls under the M is even case, and 4 levels are plus A minus A plus 3A minus 3. Correct? I just decide that straight forward from this equation, like AK equal. Now, let's see how this looks like. M is 4 because if you make the group of two bits at a time, right? Right? How many possible combinations? 0, 0, 0, 1, 1, 0, 1, 1. Yes, right. Uh, when I make a group of 2 bits at a time, I can have 4 different possibilities. Correct? So 0, 0, 0, 1, 1, 0, 1, 1. So at the same time, you can even go for 3 bits, right? That's left to us. But just an example, I took 2 because already we have considered one modulation technique which used 2, correct? So here also I'm taking the same thing, but definitely we can consider, yeah, we can make a group of 3. We can make the group of any other number, no problem. Okay, so then this will change, right? Just pick up so many levels from whether M is even or M is odd, right? So for example, if I get 6 different levels, then I should use these 6 levels, correct? Like, for M is equal to 3, we have to use 0 and plus or minus 2e if you require only 3 levels. Okay, yes, it's like that. Then so let's now say this is A, this will be 2A, and this is 3. So same thing on the other side. This is minus A, minus 2A, minus 3. So I have to divide the time axis into equal pieces. Okay, so this is T. The duration of the time axis has to be uh, split into exactly T seconds. This is first important point. So since I have only 3, what you call these things, 3 different symbols to be sent, I can use the following technique. So let's, anyway, you can assign any value to any one. So let me assume the 0, 1 is, so 0, 0 is the lowest one. Okay. So this, I'll write. If you have a 0, 0, that comes to the lowest one. Okay. Then I can write 0, 1. Then I can write the topmost one as 1, 1. And this is 1, 0. You can see the gap between each of the layer, each level is actually, right, 2A. Correct? Right. Now, so first one is 0, 1. So it should start where? It should start here. This is my first symbol. Okay. Then I can see the next symbol is 1, 1. So this is the next level that you are transmitting. And the last symbol is 0, 0. So I know that the 0, 0 is over here. So you can see the rectangular pulse that is actually being transmitted looks like this. Again, this is an example with the M4, right? M can be changed to any other value so that, right, we get any M array system. This is 0, 1, this is 1, 1, and this is 0, 0. The important point here being the time. So every gap is same. Okay, so this is capital T. This is also capital T. So even this is capital